Hello and welcome to the course Signals and Systems. I am Dr. Zishan Karim from Electrical Engineering Department, CUIUA campus. In this video, we will discuss Laplace transform in detail and compare what is the difference between Laplace transform and the Fourier transform, as we already covered Fourier transform in the previous videos. Okay, let's introduce the Laplace transform. As you know that the Fourier transform are extremely useful in the study of many problems of practical importance involving signals and LTI systems. So purely imaginary complex exponential, for example, S is equal to j omega. So j omega, you know that it is a purely imaginary complex exponential, right? So a large class of signals can be represented as a linear combination of complex exponentials, and complex exponentials are eigenfunctions of the LTI systems. We already discussed this before, how they are eigenfunctions and what are eigenfunctions, we already covered. However, the eigenfunction property applies to any complex number S. We are now taking any complex number as S, not just purely imaginary. Here this is a purely imaginary one because S is equal to j omega, and now on we will discuss not only the imaginary part only but the complete complex number. This leads to the development of the Laplace transform, where x is an arbitrary complex number. So Laplace transform is the generalization of the continuous transform Fourier transform, continuous time Fourier transform. So you can say that for Fourier transform, when is taken when you have only complex exponential like the purely imaginary one, whereas when you have a complex number, then you will move to the Laplace transform. So it is a kind of a replacement or generalization of continuous time Fourier transform. And Laplace and Z transform can be applied to the analysis of unstable systems, signals with infinite energy. So usually Laplace and Z transform we apply to the system which are unstable. Unstable means they have infinite energy, and they play a key role in the analysis of the system stability. So these transforms are very much useful to help us to bring the system to discuss the system stability, that whether the system is stable or not. So Laplace transform and Z transform are very much helpful. So what is the difference between Laplace and Z? So Laplace is used for the continuous time case, as we already studied that the Fourier series and the Fourier transform difference. There was a the discrete time Fourier transform and the continuous time Fourier transform. So there was a two type of Fourier transform before, right? So similarly, for continuous time, we usually take the Laplace transform, and the Z transform are a kind of a transform which we use for the discrete time cases. So we will cover the Z transform later in the lectures, right? So Laplace transform converges the signal by multiplying by monotonically increasing or decreasing exponential function. So we will see what are these monotonically increasing or decreasing functions. It allows us to work with algebraic equation instead of differential equations. So previously we have a complex differential equations, but in Laplace we can just manipulate or work on the algebraic equations as well. So these are some benefits of using Laplace transform. And the difference summary is that the difference between Fourier is and the Laplace is that the Fourier is the purely imaginary, right, like this one, whereas the uh, Laplace S has both the real and the imaginary part, like it's a complete kind of a complex number. Okay, Laplace transform. Let's start Laplace transform. So the response of an LTI system, you know that LTI system. So this, for example, this is linear time invariant system. So when you input x of t here, so you will get output as a y of t here, right? This will be output. And this one, LTI system response is called the impulse response, right? So whenever you input impulse here, so the response of the system will be impulse response, right? then output will be impulse response yt. So let's start. The response of an LTI system with impulse response ht. So whenever you have an impulse response given as ht to a complex exponential input, so whenever you input the complex exponential e of s of t, so complex exponential e of s of t instead of x of t, you input e of s of t here, right? And then the output will be yt, right? Yt equals to hsest, right? So as we know that yt is generally written in this way, yt is equal to, you know, that h x of t into convolution of h of t, right? We already studied this many times before, right? So in case of including the complex exponential, so we have a yt here as a hsest, right? This is your input and this is your complex, this is your impulse response uh, in S domain, right? Where h is a complex number and hs, so where hs is, if you evaluate this hs, which is equivalent to minus infinity to infinity h of t e minus st dt. So we can replace this with this number as well, right? So where h is a purely imaginary and this is the Fourier transform. So when you have s instead of s here, you have only j omega, right? J omega is purely imaginary. If you have a j omega t, e minus j omega t, then this part will called a Fourier transform, right? You already studied, right? If you replace this one with e minus j omega t and ht, so it becomes Fourier transform. When x is complex, then this is the Laplace transform of h of t, h of s. So h of s is the Laplace transform of h of t, right? So you can find the Laplace transform by using h of s is equal to x of h of t e minus st is the Laplace transform, right? So this one is the Laplace transform. For case when you have a s is a complex number, right? When s is a complex number, then h of t e minus st gives you Laplace transform, right? So the Laplace transform of a general signal x of t, if you generalize this one, you can write that x of s is equal to x of t e minus st dt, right? As a case of as in the case of the Fourier transform, we wrote x of t e minus j omega t dt, which is x j omega, and is usually expressed as x of t Laplace x of s. So whenever you take the uh, Laplace transform of x of t, then you will get x of s. So this is Laplace transform. Now let's see what's the key difference between the Laplace transform and the Fourier transform. The Fourier transform is the Laplace transform when s is purely imaginary. As we already discussed, when you take x as j omega only, so j omega is is pure imaginary, then the when s is pure imaginary, then whenever you take the Laplace transform and whenever you take the Fourier transform, result will be similar. So x of s is equal to f of x of t in the case of pure imaginary, right? An alternate way of expressing this is that when s is omega sigma plus j omega. When s is not pure imaginary and it is a complex number, so then x can be written as a real plus the complex, right? It's imaginary, real plus imaginary part. So let's evaluate in this case. So x of x sigma plus j omega, limit minus infinity to infinity, x of t e minus st. So instead of s you put sigma plus j omega, and then x of, just to separate these two terms, e minus sigma t and e minus j omega t, right? So by separating x of t e minus sigma t is into e minus j omega t, right? And let's name this term, this complete term, as x bar t, right? Then we can call x bar t equals to e minus j omega t dt. So it is equivalent to Fourier transform of x bar t, right? So the Laplace transform is what we concluded that the Laplace transform is the Fourier transform of the transformed signal x t e minus sigma t. So we concluded that Laplace transform is a kind of a Fourier transform, but for the signal when x of t is multiplied by some decaying exponential or the rising exponential. When it will be decaying or rising, so when depending on whether sigma is positive or negative, this represents growing or negative or decaying, which is not negative, or the decaying signal. So Fourier transform and Laplace transform are similar when x of t e minus sigma t is when you multiply x of t with some exponential and then you take the Fourier transform, it will be similar to the Laplace. Laplace transform is similar to the Fourier transform. Now let's discuss example number one to find that this example will help us to conclude that what is the benefit of using Laplace transform and what is the what we can't achieve in case of the Fourier transform, how we can achieve in the case of a Laplace transform. This is we are talking about convergence here. For example, consider the signal x of t e minus a t u t, which we already did in the Fourier transform as well. So the first one, the Fourier transform of this signal. So Fourier transform x j omega converges for a greater than 0. We already studied. So put here x of j omega e minus a t u t e minus j omega t dt. This is general formula. So we put instead of xt e minus a t u t. So by removing u of t, the limit changes to 0 to infinity instead of minus infinity to infinity. So it becomes e minus at e minus j omega t. And by taking the integration of this and solving it further, we will get uh, 1 over j omega plus a. We already solved this in detail in the previous example, so you can refer to that example for more detailed steps how we get 1 over j omega plus a, right? And this is only valid, you remember that this is only valid when a is greater than 0. So if a is not greater than 0, a is less than 0, then Fourier transform will not converge, and it means that what it means that the Fourier transform is not possible when the signal when a is not greater than 0. It means when a is less than 0. So the Fourier transform of a signal will not be possible in that case. So now take the Laplace transform of the similar signal, same signal. So x of s e minus a t u t e minus st. Instead of omega t, we have st here. So let's combine both of them exponential terms together and replacing the by replacing u of t, we are updating the limit from 0 to infinity. So it becomes e minus s plus a t dt. And as you know that s instead of s we can write that s is equal to sigma plus j omega, right? Sigma plus j omega. So we are replacing s with a sigma plus j omega. So when you replace that and then reshuffle these terms, so it becomes e minus sigma plus a t, and by separating e minus j omega t, why we are separating to write in terms of Fourier transform in the shape of a Fourier transform. So which we can notice from here that which is the Fourier transform of e minus sigma plus a t u t, right? Uh, Instead of uh, x, you can see that if you name it x, right, and the limit is 0, so it becomes e minus sigma plus t u t. So finally, it means that x of sigma plus j omega is equal to x 1 over sigma plus a plus j omega. In the previous term, you have only a here, right? E minus at, right? So you got a in the denominator, right? And instead of a, we have sigma plus a, right? The difference is sigma plus a. So we got sigma plus a in the denominator plus j omega. And the condition here here the condition was a is greater than 0, but here instead of a we have a sigma plus a. So sigma plus a is greater than 0. So if a is negative or 0, for example, if you have a which is negative or 0, right? You replace a with some negative number or 0, then Laplace transform still exists. However, Fourier transform doesn't exist. So it means that Laplace transform is valid for the negative and 0 as well. Whereas for similar function, Laplace transform was only valid for a positive a, right? So here the Laplace works for a negative and 0 as well. So uh, by replacing sigma plus a with sigma plus j omega with s, because you know the sigma plus j omega is s, so we can write s plus a as well. So this sigma plus j omega is replaced by s, so we can write 1 over s plus a. And you know that if you move this keep sigma here, and by rewriting this equation, for example, sigma is greater than minus a, it is similar, right? Because is greater than 0, when you move this a to this side, it becomes minus. So sigma is greater than minus a. Where sigma, you know that if you take the real term of s, so sigma is the real part of s. So it is equivalent to, if you take the real of s, it is equivalent to sigma, right? As here I discussed. Since sigma s is equal to sigma plus j omega, and the real part of s is sigma. So you can just write, instead of sigma, you can write the real of s should be greater than minus a. So we found that, we concluded that for e minus a t ut, you have a Laplace transform s 1 over s plus a, where real of s should be greater than minus a. This will be the condition, right? And we also concluded that for a negative or 0, the Laplace transform still exists. For example, if we take in the previous equation a equals to 0, then what happens? Xt, because previously you have a e minus at, in the previous example, e minus at ut, we have a function this one, right? And if you make a is equal to 0 here, it will only becomes unit step function, right? X of t becomes unit step function, right? By putting this 0, it becomes 1, so only unit step function will remain. So for example, when a is equal to 0, xt is a unit step function. So what will be the Laplace transform of unit step function? As you know that Laplace transform of e minus at was uh, 1 over s plus a. So when a is 0, so what will you get? 1 over s only. So by using this example, we concluded that for a unit step function, Laplace transform is 1 over s, and the real of s should be greater than 0. Why real of s should be greater than 0? You know that sigma plus a is greater than 0. So when you put 0 here, so it means that real of, because sigma is the real of s, so real of s should be greater than 0. So this term in this way, we can write in this way. We know that in particular, just as the Fourier transform does not converge for all signals, the Laplace transform may converge for some values of real, not for others. So in equation, the Laplace transform converges only when sigma or the real is greater than minus a, and if a is positive, then x can be evaluated at x is equal to 0. What does it mean? It means that previously we saw that in the previous example, we have real of s should be greater than minus a. So when we take a positive, so a positive means that you know that sigma plus a should be greater than 0, right? So to consider a should be positive, it means that a should be greater than 0. So to make it positive, we will take as an example sigma as 0. So when you put sigma 0 here, it becomes a greater than 0, right? So for a greater than 0, it means a positive. What will be the Laplace? X of 0 plus j omega 1 over j omega plus a. So as indicated in equation, for sigma is equal to 0, the Laplace transform is equal to the Fourier transform. So when we took a is equal to 0, sigma is equal to 0, in this case Laplace transform is equal to the Fourier transform, and is evident from the preceding example. And if a is negative or 0, the Laplace transform still exists. but the Fourier transform does not. So we concluded that Laplace transform exists for the negative value and the zero value as well, and for the positive value, for example, a greater than 0, it is equal to the Fourier transform. Let's take another example. X of t equals to minus sign here. So minus e minus at u minus t, and we have a minus sign here as well. So Laplace transform, uh, you know that x of t into e minus st. So just put these values here. So minus, we will take this minus outside the integral, minus infinity to infinity, e minus at, e minus st, and u minus t. So as u is minus t, it means that its range will be from minus infinity to 0. Direction will be opposite. So minus infinity to 0, and just combine these two terms, right? So take negative sign common. So we will get e minus s plus a t dt. And as you know that previously you find that we have a e minus s plus a t is equal to 1 over s plus a. So uh, the result is similar. So convergence requires that real s plus a should be less than 0, or real of s should be less than minus a. So the Laplace transform is identical to example 1. We can, by just putting, if you take the integral and then put these signs, and finally you will get this result, right? There are some steps included here which I missed here, so you can just put the limits and you will get the similar result. So what we want to uh, do here or discuss here about the region of convergence. For example, in the previous example, you get the 1 over s plus a. And here, with different x of t, you are still getting 1 over s plus a. So what is the difference between these 1 over s plus a? So convergence requires that here real of s plus a should be less than 0. Previously, real of s plus a was, it means the real of s was greater than minus a, right? Here they are talking that real of s should be less than minus a, this one. So this is the difference. So the Laplace transform expression is identical, similar but different signal. However, the region of convergence of s are mutually exclusive, that is non-intersecting. Previously, they were the result is similar, but the region of convergence is different. So for a Laplace transform, we need both the expression and the region of convergence. So to properly understand and properly interpret uh, a Laplace transform, it is not only required the expression of x of s or the Laplace transform, but we also need the region of convergence as well. So let's discuss what is region of convergence first, and then you can understand the difference. So region of convergence. So region of convergence of Laplace transform is the set of values for sigma plus j omega for which the Fourier transform converges. So these are the set of values for which the Fourier transform converges, means the Fourier transform exists. So region of convergence is displayed by drawing separating line or curves in the complex plane, because as illustrated in below, for example 1 and 2. For example, this is for example 1. So this is your imaginary axis. Imaginary means j omega, right? And this is your sigma. Real means your sigma. So sigma and imaginary j omega. So you can notice that for the example 1, real s was greater than minus a. The condition was real of s should be greater than minus a for the existence of the Laplace transform. So it means that the region of convergence will be in this way, like in this direction, greater than minus a. Whereas for this example, we have a region of convergence uh, which exists for real of s when it is less than minus a. So in this direction, right? If you have a real of s greater than minus a, then the Laplace transform of that function doesn't exist. So what we concluded from here that uh, only the equation is not enough to understand the Laplace transform. We also need the region of convergence where it lies. Otherwise, you cannot properly find the Laplace transform. It's another example uh, about the Laplace transform. You have a given signal x of t sine omega t ut. Let's put in the general equation x of s equals to minus infinity to infinity, and instead of sine omega t you can write 1 over 2j e j omega t minus e minus j omega t ut, and this is general e minus st dt, right? And whenever you have a ut, your limit will change from 0 to infinity, right? So use 0 and combine these two terms like e minus st and e j omega t, and take 1 over 2j outside the integral. So we can write e minus s minus j omega t for the first one, minus e minus s plus j omega t for the second one, like combining these two terms, second one, and this one is the first one. And now take the integral. When you will take the integral, it will become e minus s minus j omega t over, due to this minus sign, you will have a minus s minus j omega. So from 0 to infinity. So similarly, when you take this integral, so it becomes e minus s plus j omega t over, you have a s plus j omega, right? And because y is x plus uh, this minus and this minus will become plus a, right? So only s plus j omega. Now you put values of infinity and 0. So when you put infinity, first term becomes 0 because e minus infinity is 0. So 0 minus this one, so minus minus become plus. So it becomes 1 over s minus j, and these terms become 1 over s plus j, right? Because infinity first one 0, and then you put minus second one. So due to this minus, you have a negative sign here, right? Now take the LCM. So LCM s minus j omega s plus j omega is s square plus omega square, and from here you will get s plus j omega, and from here you get minus s minus j omega. So the s terms will cancel out, and finally you will get 2j omega here. And this 2j will be cancelled out, so you will get finally omega over s plus s square plus omega square. So here the condition is that real s should be greater than 0 to converge for the convergence of a Laplace transform. So similarly, you can take numerous other examples for practice and how it works and how you can solve. And for solving more and more, you can have a more grip on the Laplace transform. This is another example. Now you consider a signal that is the sum of two real exponential. What is the sum? Because some are different. So this is exponential, and this is another example, exponential. So two exponential. In this case, let's take the Laplace transform. So 3e minus 2t minus this. You have instead of xt, put this one, and e minus st dt. Just separate these two terms. So e minus 2t, e minus st dt minus 2e minus this one, right? Using example 1, you know that we calculated instead of at, now you have a 2t, right? So it means a is 2 here. So Laplace transform will be 1 over s plus a, right? So instead of a, you have a 2 here. So 3 is outside. So we are taking help from the previous example. You can just say 3 over s plus 2, and from here a is minus a is 1, right? Minus 1, a is 1, right? And so minus 2 over s plus 1. The Laplace transform is minus 2 over s plus 1. Now the region of convergence illustrated with these terms are real of s should be greater than minus 1. So in this case, the condition is that real of s should be greater than minus 1. And for the this term, the condition is that real of s should be greater than minus 2. Right? Because previously real of s should be greater than a, and real of s should be greater than a. So here instead of a you have a minus 2, and for here you have a minus 1. So whenever you have a, it means that the both will converge for real of s greater than minus 1. So because minus 2 is less than minus 1, so it means that we can only say that the Laplace transform will converge when real of s is greater than minus 1. So the Laplace transform is this: by taking the LCM or multiplying these two terms, s plus 2, s plus 1, so you will get s square plus 3s plus 2, and on the top you will get x minus 1. So this is your x of s, which is equal to s minus 1 over s square plus 3s plus 2. Now discuss the concept of the poles and zeros. The poles and zero, what is difference between poles and zeros? So whenever you have a Laplace transform, there is one numerator term and other is the denominator term. As we already discussed in the previous example, we have a two terms. So the roots of the polynomial in the numerator of f of s are 0. So these are called zeros, right? Whenever you have a roots of the polynomial in numerator, n is for numerator and d is for denominator. So numerator terms represent zeros and the denominator terms represent poles. So these are zeros and these are poles. So take let's see how it looks like. For example, f of s is the Fourier transform of 10 s square plus 3s plus 2 s cube plus s 17 s square this one. So this is numerator, this is denominator. So we can write this numerator term separately as s plus 1 and s plus 2, and we can evaluate this one or simplify this one in this way: s plus 4, s plus 5, s plus 8. Now let's plot them in the s plane. So s plane means j omega complex and the real. So s plus 1 means s is equal to minus 1 and s plus 2 means s is equal to minus 2. So this is negative axis, right? Negative. So zeros, because the numerator terms represent zeros, so we represent zeros with the circle, right? So lies at minus 1, first 0 lies at minus 1, other 0 lies at minus 2. And here denominator terms are poles. So first s is equal to plus 4 means s is equal to minus 4, s is equal to minus 5, s is equal to minus 8, right? So minus 4, first pole rise at minus 4, other at minus 5, a third one at minus 8. So the numerator, the zeros are the roots of the numerator are s is equal to minus 1, minus 2. The poles are the roots are minus power, minus 5 and minus 8. So these are poles and zeros. And what are the importance of using these poles and zero? Let's discuss on next slide. This is another example just for understanding that if you have a Fourier transform of Laplace transform of e minus at ut, then you have a Laplace of f1s is equal to 1 over s plus alpha. So here you have a zero, nothing on the top, like the no zeros, because it is 1 only. So only you have a one pole which lies at minus alpha, right? So you have a pole only, right, on the complex plane. So now discuss what we can get from poles and zeros and what does it mean. So for causality and stability, as I discussed in the start that by using Laplace transform and Z transform, you can judge the stability of the system and the causality of the system. So for a system to be causal, right, causal, and all poles of its transfer function must be right half of S plane. So this one, right half, this is right half, this is left half. So if you want to check whether the system is causal, so you will find the poles, and if poles lies on this plane, right half the planes, like this one, two poles we have on the right half, it means that the system is causal. And if you want the system to be stable, so when it will be stable, when all poles will lay on the left half, so this is left half of the S plane. So when it lies on the left half, it is stable, right? So causal right half, stable left half. Third one, if you have a system which has a poles which lies on, it is called marginally stable when at least one pole of its transfer function lies on the j omega plane, like this plane, right? J omega. Like it means that they have only a complex number, not a real number, right? So whenever you have a one pole here, so it means that the system is marginally stable. So these were the benefits of using poles and zeros, right? You can judge the stability and causality of the system. So these are some summary of the basic Laplace transform pairs. For example, x of t is impulse. It means that x of s is 1. So they have poles none and region of convergence is greater than minus infinity. So no poles and region of convergence is greater than minus infinity. And unit step function, we already saw that it has the Laplace transform 1 over s. So pole is at s is equal to 0. 1 over s means pole is at s is equal to 0. And it means that real s should be greater than 0, right? And the other one is minus unit step function, minus u minus t. It has same 1 over s, right? But and the pole lie at the s is 0, but this is stable. Its region of convergence is for the sigma less than 0, right? So the difference here is the region of convergence. And we already saw E minus AT UT, we have 1 over S plus A. So pole lies at minus A, and the region of convergence is greater than minus A. For the minus, similarly, we have x of S 1 over S plus A, and the pole is at S minus A, whereas region of convergence is on the opposite direction, like less than minus A. Some other pairs you can just go through and see what does that mean, right? This is just E sigma T U T, same 1 over, instead of A we have a sigma, so S minus lambda, and here instead of minus we have a plus, so here you will get minus sign, so on, right? You can just go through. Thank you for listening, and for Q&A session we have an online separate session. Thank you very much.